Okay, so let's talk about probability in general. Oh, Susan's having a problem hearing this. Okay, so I'm going to go ahead and get started. I'm going to start out with just talking about the general idea of probability. It's pretty obvious to most of us that there's a lot of events, random events that can occur that we can predict what the probability or predict the likelihood of those events occurring. So for instance, if I flip a coin, you know that the chances there's only two things that can happen. It can come up heads or it can come up tails. So the probability on any given toss of a coin that's going to come up heads is going to be 50%. Okay, the next thing you can probably intuit is that if I flip a coin twice, the probability will come up heads the first time is 50%. And the coin not having a memory and the two tosses being what we would call in statistics independent events, the second toss of the coin, the probability of its coming up heads would be 50% as well. So, oh, good. Okay, we got everybody online now and can hear. If you can imagine, let's say we want to know what's the probability of, if we toss a coin twice, of both of those outcomes being heads. Okay, well, first time it's 50%, second time it's 50%. So the probability of that occurring, that we had heads on both tosses, is going to be 0.5 times 0.5, or 0.25, about 25%. So what's the probability of getting three heads? Toss it three times, it's going to be 0.5 times 0.5 times 0.5. It's a multiplicative relationship. So it's going to be 0.25 times 0.5 times 0.5 times 0.25 is going to be 0.125, or 1 in 8. Okay, 1 in 2 is going to be the first possibility, 1 in 4 is the second, 1 in 8. So that's pretty intuitive. Okay, so now if we started to look at probabilities that don't involve only outcomes like heads or tails, it gets more complicated. For instance, what if I asked you, if I flipped a coin three times, what's the probability that I would get two heads? Okay, so there's a lot of ways that can happen. I could get heads, heads, tails. I could get tails, heads, heads. I get heads, tails, heads, and so on and so forth. Let's actually take a look at what that might look like if I laid out all of the different possibilities. Okay, I'm going to open up a notepad here so that I can actually go through all of these things. Oh, don't look at that. We're getting ahead of ourselves there. Don't be frightened by those formulas. Okay, so I'm going to take a look at this. Okay, let's take a look at all of these different possibilities. Okay, first thing that can happen on the first toss is I can get either heads or I can get a tail, right? So I start off, there's a 50% chance of getting a head and a 50% chance of getting a tail. Well, let's say that first toss is heads. So I'm going to draw something called a probability tree here. So if the first toss is heads, now I have, for the second toss, two probabilities as well. I have 50% chance I can get another heads, or 50% chance I can get a tail. And over here, if I got a tail, there's a 50% chance. I never leave myself enough room here. So 50% chance I could get a heads after that and a tails after that. So again, 0.5 times 0.5. How about the third toss? So third toss, if I got heads, heads, the next possibility would be, again, 0.5 for heads and 0.5 for tails. And for tails, it would be, again, heads or tails. It would be the next one. For this one, it would be heads or tails. And for this one, it would be heads or tails. All the probabilities would be 0.5. Okay, so let's take a look at what's the probability of getting three heads. In other words, this outcome is heads, heads, heads. So I go straight up the tree here. 0.5 times 0.5 times 0.5 is 0.125. Okay, well, how about if I go this direction? Heads, heads, tails. Well, this is heads, heads, tails. That probability is 0.125. Right? How about we go here? Heads, 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 we did those two. So now heads, heads, tails, heads, that's going to be heads, tails, heads, and this is going to be heads, tails, tails, and this is going to be tails, heads, heads, and tails, heads, tails, and this is going to be tails, tails, heads, and tails, tails, tails. And all of these, by nature of the fact that it's 25% probability, all of these outcomes are going to have a probability of 0.125. Okay, and with 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes, if I add up all the probabilities, what am I going to get? Anybody want to comment on that? What do you think I'm going to get if I add up all those probabilities? I've determined all of the different possible outcomes. So if I add up all of the different possible outcomes, probability is going to be 1, exactly right. So 1/8, 1/8, 1/8, 1/8. 1 out of 8, 1 out of 8, 1/8, 1/8, 0.125. Any way you want to look at it, it's going to add up to all the probabilities are equal to 0.125. So my initial question was, what's the probability of tossing 3 coins and getting exactly 2 heads? So this doesn't qualify. This does qualify. This qualifies. This doesn't qualify. This does qualify. This doesn't. This doesn't. This doesn't. So the probability, there's 3 ways for us to get 2 heads if we toss a coin three times. So the probability is 37.5% or 0.375. Okay, so this probability tree thing works out pretty well for us. In fact, it'll work out also if I look at it from another perspective where say the probabilities are not exactly the same. So for instance, let's say that a student takes a test and he answered 3 questions. Right, 3 questions. The probability of getting the first question right is 0.5. Probability of getting the second question right is 0.8. That's an easy one. Probability of getting the third question right is 0.2. Okay, so all different possibilities. So we can say to ourselves, what's the probability of getting 3 right answers here? And I could build a probability tree again. So the first question, you could get it right or wrong, and probability of getting it right is 0.5, probability of getting it wrong is 0.5. Now on the second question, we diverge a little bit. This time, the probability of getting that one right is 0.8, right? That's the correct answer. An incorrect answer, probability of that is only 0.2, right? So now you can see things are going to be different in this probability tree. Now, so the example I gave you, what's the probability of getting all right answers? That's easy because that's going to be 0.5 times 0.8 times 0.2. So we can just multiply those. Okay. On the other hand, what's the probability of getting all wrong answers? Well, the probability of getting all wrong answers is going to be 0.5 times 0.2 times 0.8, right? The opposite, the inverse probability of getting them right. So that's going to be easy to determine. What's going to be complicated is the ones in the middle. So now this isn't that bad because I could do this with a probability tree and come up with any combination I was interested in without too much trouble. However, what if I asked you the probability of a person having diabetes in a population is equal to 10%, 0.1. If I asked you, what's the probability that that if you select 3 people at random, that all 3 will have diabetes? Well, that's going to be 0.1 times 0.1 times 0.1, or 0.001, right? So what's the probability of none of these people having diabetes? Well, the probability of one of those 3 people having diabetes, not having diabetes, is 0.9 because 90%, 10% chance they'll have diabetes, 90% chance they won't. 0.9 times 0.9 times 0.9 will be the probability that none of the 3 have diabetes. So it's easy if we're looking at all of them or none of them. But if I asked you, what's the probability that 3 out of 10 would have diabetes? Well, now I would have to build a probability tree which starts out with 10 choices in the beginning, and second level 10 more, and third level 10 more. So it's going to be very difficult to do that. Fortunately, not this week, but in coming weeks, probably next week or the week after, we're going to be looking at how to determine this using a formula and a distribution called the binomial distribution. Binomial means that there's two choices. So anytime there's two choices, there's a certain kind of technique that we can use to determine these probabilities based on two choices, probabilities for two choices. So we're going to be looking at that as we move forward. So, but that's kind of what we're starting with here. Easy enough when we're dealing with all or none, based on knowing what the probability for any particular individual is. Okay, so let's move on from that a little bit. Take a look at what the next thing that I wanted to review. Okay, so we got coin tosses, random population. Okay, I think we went through that pretty well. Any questions on that so far? Right, that's pretty simple, right? It's kind of a prep for what we're going to do going forward here, but even more so for stuff that's going to come up in the next week or two. And here's another way. Here's just formulated the same way, except a little bit neater. Okay, and that you can actually go through these on your own and actually figure out these probabilities for, in this case, actually, in this example, the probability of getting a correct answer is 0.2. It's the same on each one of these questions. Like if you take a multiple choice question with 5 answers, probability, if you don't know if you just guess at it blindly, it's going to be 1 in 5 or 0.2. So this is kind of what your likelihood of different outcomes would be. And then you could repeat that tree again, except this time you could, on your own, give this a try and see if you can do it with the probability of getting question 1 correct being 80%, question 2 50, and question 3 90, to see how it affects the probabilities. And you can list them there. Okay, so you can give that a try on your own. Okay, so I'm going to look at probabilities now from a little bit different perspective. And this kind of ties into Levi's lecture and the idea of another kind of probability, which is a conditional probability. Okay, and a conditional probability, what we're examining is what's the probability of something occurring given that something else has occurred before it. Okay, so for instance, if we randomly pick a person from this population, and this is the marital status of the U.S. population a decade or two ago. And this represents all adults in the United States over 18 years of age, and these numbers represent a number of people, in fact, number of millions of people. So this represents 29.7 million people, and in fact, the total population at the time that the survey was done, and it came from the census presumably, of people over 18 was 214 million people. So these are actual counts of people. So if we would randomly select someone from this population of 214 million people, what's the probability that person that we would select is divorced? Okay, what do you guys think would be the probability that we would randomly select a divorced person? So now you could actually give me the percentage or the proportion. Okay, we can actually work it out. Or if you want, type it in there and tell me what you think the proportion is. If you don't have a calculator handy, just type in the numbers that would represent the numerator and denominator for a fraction. Okay, yeah, exactly. We have 214 million people in the total population, and we have 21 million people that are divorced. So it's roughly about 10%. Okay, so that looks good, right? That's pretty easy to interpret. Okay, now find the probability that a person in this population happens to be male. Okay, what's the probability that a person, randomly select a person, maybe you just randomly pull a social security number out of a hat, and that person would be male. Okay, well, let's see. We have, how many total males do we have? It's 104.9 males out of a total population of 214. And I say, yeah, about 49% is what you would wind up getting. Okay, guys, got that? I'm more interested that you see where this came from in this table. Okay, next, find that the probability that the person is both a male and a widower. Okay, now as we think about that, I want you to think about what that means in terms of the probability group, the Venn diagrams that we were looking at before. So that person is both a male and a widower. He has to satisfy both of those conditions. Okay, that means that we're only looking at people out of the total population. We're only looking at people that are both male and widower. Would that represent the intersection or the union of males and females? Intersection is when that U is turned upside down, right? And union is when that U is turned upside down. The probability that a person is both male and a widower, is that the intersection of the probability for male and widower or the union? Let's see what opinions we get. Okay, intersection, right, because it's only people that satisfy both of those conditions. Okay, so let's take a look at that. So we have males, all the males are in the top row, and the widowers are only in this cell here. So the only people that satisfy the condition, widower and male, is 2.7 out of the population of 214 million. So it would be roughly about, I guess, 1%, right? Okay, whatever 2.7 divided by 214 comes out to be. If I had said phrases differently and said find the probability that a person is male or a widower, that would be the union, right, turned upside down, of male, a probability of being male and probability of being a widower. So that would be, let's see what that would be. That would be anyone that's male would be qualified, so that would be 104.9 plus the females that happen to be widowed, which would be 11.3. So the union would be 104.9 plus 11.3 added together, divided by 214 million. So I'm guessing that would probably be around about 55% or something like that. Okay, I'll leave it to you guys to actually do the calculation and figure that out. Now, this last example is what we would call a conditional probability. Given that a person is male, what is the probability that he's married? Okay, anybody want to hazard a guess on that? Given that the person is male, what's the probability that he's married? You can almost look as a conditional probability as a filter. In other words, we're filtering out all, given that a person is male, so we're filtering out all of the females. That's our condition. Okay, so we're only going to look at people that are male. So we're only going to look at 104. So our denominator is going to be 104 instead of 214 because we've limited our examination or our population, qualified population, to only males, 104 million. Okay, and what's the probability among that group that he's married? And we have 63 million out of 104 million, so it's roughly about 62%, 61 or 62%. Good. It looks like you guys are catching on to this pretty quickly. So I mean, when we threw a lot of formulas, a lot of Venn diagrams on the up during the lecture, but when you start to look at this in terms of what it means and how it impacts us in terms of our understanding of probabilities and sampling and so on and so forth. And there's a few important words that we're learning here. For instance, independent samples, right? So we want to make sure that our samples are independent of one another. In other words, they're like coin flips, where the coin doesn't remember what the last flip was. And if there's a large population, that's pretty easy to do. Okay, so now let's take a look at a situation where maybe probabilities are not independent. Okay, so let's say that I'm going to randomly stop people on the street and ask them if they have insurance. Okay, so I stop a person on the street. Do you have insurance? And they say, yes, I do. Next person, do you have insurance? No, I don't. Do you have insurance? Next person, do I have it? Is each one of those people I'm stopping on the street, is that really an independent sample? Is each one of them individually an independent sample? Anybody want to give me an opinion on whether they think that might be an independent sample? No, I don't think so either. Think about this. Now, somebody walking on the street together might be related, right? So if you have a husband and wife walking on the street and you ask each one of those two people if they have insurance, a lot of people have insurance as a family or a child and a mother and so on and so forth. So the second person that you're asking may be related to the first, and that may not really be an independent sample. So we really want random independent samples. It's important that we understand that when we're doing sampling work. Later on, when we get into study types and so on and so forth, that'll come up. That'll be a lot more uh, uh, well defined for us as well. Okay, so I'm gonna put away this idea of probability for right now, and I'm gonna move on to this idea of diagnostic tests. You got a pretty good introduction to diagnostic tests just a little while ago. Okay, and I'm going to make up, rather than work with the diagnostics test that was in the paper. That, by the way, if you look at the PowerPoint, the source of that paper, the URL on the internet for that paper is available there. If you can't find it, let me know and I'll get hold of it and I'll post it. I'll get a PDF and post it to Blackboard. But you can actually find that paper based on the URL that's in the PowerPoint. Okay, so instead of using that, because that had some relatively complex numbers in it, to make it a little bit more understandable, I'm going to create my own population and diagnostic test, actually a fake population. Now, don't freak out because I'm going to use Excel. And I know some of you guys are a little uncomfortable with Excel still, but I'm only using Excel as a calculator. Everything I'm going to do now with Excel, you're going to be able to do just as easily with a piece of paper and some note paper and a calculator. Okay, so what I'm going to do is I'm going to take a look at this diagnostic test that someone has invented. The reason I actually picked this out for a specific reason. You have a group of 100 subjects that are known to be sensitive to nickel. A lot of people are sensitive to nickel these days. The issue of allergies to certain metals, like skin allergies to certain metals, like nickel, is increasing because piercings very popular now, right? So you got piercings, you got metal, a lot of different alloys of different type, even silver, maybe alloyed or gold, maybe alloyed with other metals, but a lot of stainless steel devices like watches, for instance, back of watches have stainless steel. Stainless steel is composed of iron, but other alloying elements such as nickel and chromium and so on and so forth. And when you perspire, even though it's stainless steel, I knew a guy who worked with United States Steel, U.S. Steel, who manufactured stainless steel, and he would have customers every once in a while that would complain, I'm getting corrosion on this stainless steel and stuff like that. And I see this rust on it. What's the story? I thought it was stainless steel. And he used to tell them, oh, you got to understand, it's called stainless steel, not stain-free steel. Most of them didn't like that use of the language, but it's true. Stainless steel is not, especially when it's exposed to salt, for instance, the chlorides and salt from your sweat. It can actually corrode a bit. You can be exposed to some of the metals that dissolve in very tiny quantities, and I know that personally because I'm sensitive to it. So I'm wearing right now is only. I won't tell you how many people here. The room is almost full, so you guys are the only ones that are at home that stayed home for the class. Right now, I'm wearing an Apple Watch, and up until this Apple Watch came up, I gave up wearing watches because I was sensitive to nickel, and I would get a rash on the watch whenever it would perspire. And this one has an enamel back and a little glass thing, so it can sense it can pick up your pulse rate and stuff like that. So as it happens, it doesn't have any stainless steel in the backing, so I can actually wear the thing again. So again, as I said, people are getting piercings. A lot of those are stainless, and this is coming up more and more. So it's interesting. Maybe we'll take a look at a simple diagnostic test. The one that they use currently is a patch test, I guess, right, where they actually put a grid on your arm or something or some other part of your body, and they actually expose you. It's a challenge. They actually prick your skin slightly with the various things that you might be allergic to, and some metals might be included in that. And then they go back and look at it a couple of days later to see if you got any swelling there, and they identify what you've reacted to. Okay, that's kind of that's the only problem with that is that you take someone that could be extremely allergic to something, usually sometimes not a good idea to expose them to that as a challenge for a test. Okay, so let's say this company is interested in developing a diagnostic test that is safer for a nickel allergy. So they take a group, so they developed a test. Now they want to determine how well it works. So they might take a group of 100 subjects that they know are sensitive to nickel, that it's already known that they have a sensitivity. Now they use this new diagnostic test on them. And as it turns out, that out of that 100 subjects who we know are sensitive to nickel, 80 of those subjects test positive. So the test is right in identifying sensitive people among people that actually have a nickel allergy 80% of the time. That's referred to as the sensitivity of the test. Okay, so now that's interesting. 80% of the time it's going to get that right. Okay, so now the other end of this thing is that you want to make sure that that test just doesn't say to everybody that they have a nickel allergy. So you want to test this diagnostic test on people that don't have a nickel allergy. So you take another group of 100 subjects that are known not to be sensitive to nickel, right? And you perform the same test on them, and 90 out of 100 test negative. 10 of them test positive. And this happens. Some tests will, will give you false positive. In fact, almost any test will give you some false positives. So 90% of the time, though, it got it right. It said people that don't have a nickel allergy are negative in this test. That's called the specificity of the test. So now the sensitivity of this test is 80%, gets it right, gets a positive test. 80% of the time people have a nickel allergy. And for people that don't have a nickel allergy, gets it right 90% of the time. Okay, so its specificity is 90%. So that's the definition, basically, of sensitivity and specificity. Okay, so now I'm going to move on, and I'm going to actually set up a population now. Okay, so I'm going to look at a population that is known to be have a prevalence of nickel sensitivity of 20%. That's pretty high, but who knows? Maybe that there are populations of people that have had a lot of piercings or work around nickel or something like that. That a large percentage of them are positive. So I'm going to actually, let me go here, since these numbers are pretty simple. I'm going to actually use this instead of Excel. Okay, so I am going to randomly sample this population, and one of the outcomes that I might expect if I randomly sample 200 people, right? If the prevalence, the probability of having the nickel sensitivity, right? Probability of being sent. I'm gonna call that the disease. Probability of having nickel sensitivity is 20% in this population, 0.2. Okay, so I'm going to put together a table here. If I have a population of 200, then I would expect that out of those 200 people that I randomly selected, 40 of them would be sensitive to nickel, 20% prevalence. Okay, so I'm going to create a table over here. Okay, and it's a 2x2 table. Okay, and in the rows, remember when we talk about contingency tables in the future, or crosstabs or contingency tables, we're going to be drawing something like this. And usually in the rows, you put the diagnostic test you're performing, or you put the exposure or something like that if you're testing an exposure. But I'm going to call it I'm going to call the rows the results of our test. So people in the top row are only going to be people that tested positive. People in the bottom row only going to be people that tested negative. And people in the first column are people that are nickel sensitive, positive to the disease. And in the second column, going to be people that are negative for nickel sensitivity. So, and I'm going to add a couple of columns over here for us to do some calculations. Okay, but our main part of this table is this 2 by 2 table. Okay, and everybody in this population is going to fit in there somehow or other. So the total number of people in this population is 200, or in this sample is 200. So I'm assuming, for the purposes of our calculations, that the prevalence is 20%. So that would mean 40 people have the disease or are nickel sensitive. That would mean 160 people out of the 200 don't have nickel sensitivity. Okay, so now my sensitivity for this test, according to the manufacturer, is 80%. Okay, so if my sensitivity is 80% and I have 40 people that are sensitive to nickel, right, how many of them would I expect to get a positive test? Okay, anybody want to hazard a guess online? 40 people, you expect to be right 80% of the time, right? How many do you think I would get that test positive? Right, 32. 80% of those 40 people will test positive, and 20% of them, or the difference, will test negative, right? It's going to add up to 40. Okay, so now I'm going to look at these 160 people, right, that don't have nickel sensitivity. Remember, the specificity was 90%. So I expect to identify negatives correctly 90% of the time. So what's 90%? This is where Excel would have been a little bit nicer to use, right? Because I could actually do the calculations right in place. So if I have 160 people, right, times 0.9, right, I would expect to get the right answer for 144 people. I'm sorry I even did that, since you guys were quicker at it than I was. So how many people are going to test positive here? Okay, do I have an opinion on how many people are going to test positive there? Right, 16, difference, right? Okay, so let's take a look at this now. So now, how many people tested positive in this population of 200 people? How many positive tests did we get? Okay, we got 48, right? 32 and 16. 48 people tested positive. You guys are really catching on to this pretty quick. Okay, how many people tested negative in this population? Right, so I got 152, right? And this all agrees, because you wind up with 200 as the total population. Okay, so now I'm going to look at this idea of having taken, let's say you went to the doctor, you took this test, you got a positive result. Your next question is, well, now that I got a positive result, what's the likelihood that I actually have a nickel sensitivity? Okay, well, with the nickel sensitivity, it might not be as critical as it might be for some other thing, but if you can imagine, if you got a positive test for breast cancer, or you had, say, a mammogram, gave you a positive test, or if you take a PSA, if you're male and you take a prostate-specific antigen test, and you get a result that says that you're likely to have prostate cancer, or so on and so forth, any of these different kinds of tests. If you get a positive result on a screening test, well, now you want to know how you should respond to that. Does that mean you have the disease? Well, in fact, on most screening tests, that doesn't automatically mean you have the disease. And different tests have different, a positive result in different tests can mean different things. And in fact, it's not just a matter of the function of the test. We're actually going to look at there's other factors involved. So for this particular test, if you had a positive test, what's the probability that you actually have a nickel sensitivity? Okay, get positive test, what's the probability? Well, that's what we call the positive predictive value. Okay, so the positive predictive value of this test is going to be, well, how many people got positive tests? It's going to be number of people, the probability of getting a positive test, right, over the probability of actually getting a positive test and actually having the disease, right? So how many people actually have, excuse me, I reversed those. Should have been that one on top. But let's not look at it as a formula. Let's look at it just interpreted as functionally. So 48 people had a positive test. Out of those 48 people, only 32 actually had the disease, right? So the probability of any one of them having a nickel sensitivity is 32 over 48. So the positive predictive value of this particular test in this particular circumstance is going to be 32. Whoops, 32. They're way ahead. You guys are way ahead of me. Divided by 48. Okay, and that's going to be about 67%, right? So there's a 2/3 chance that you have nickel sensitivity, but there's a 1/3 chance that you don't have nickel sensitivity, right? So I'm going to do something interesting here. I'm going to redo this, exactly the same test. Okay, I'm going to do this again. Okay, here's my 2x2 table. And I'll extend this out so we get our totals. Okay, positive diagnostic test, negative diagnostic test, have the disease, don't have the disease. Okay, so now this time I'm going to take our 200 people. I'm going to change the specificity, the sensitivity is still 80%. The specificity is still 90%. Nothing's changed. Only thing I'm going to change now is the prevalence. I'm going to say that the prevalence is equal to, let me think about this for a second. Prevalence is equal to 5% in the population. Let me see if that's going to work out okay. See if we can get it even lower. Okay, I'm going to say 200, and we get 5. 1% would be 20, 1% would be 20. Hang on a second, 10, 2, that'd be 2. Okay, let's say 5%. I'll stick with 5%. Okay, so if the prevalence is 5%, out of my 200 people, how many of them are going to have a nickel sensitivity? Well, 5% of 200 is 10 people, right? So that would mean 190 people are not sensitive to nickel in this population. I'm going to make it even more dramatic. I'm going to make it, my prevalence is 2.5%, right? Prevalence is 2.5%. That means that this is 5 people and this is 195 people. Okay, so now if I get it right, people that have nickel sensitivity, if I get it right 20% of the time, right, and there's 5 people that have nickel sensitivity, that means I'll correctly predict that 4 out of those 5 people have nickel sensitivity. Okay, so you guys see what I did there? I just made it prevalence 2.5%, so I made this number 5. Okay, so what's the probability that you would get a negative test for someone that has it? Well, you get it 20% of the time, or 1 out of 5 times, right? So one of them would test negative. Okay, let's take a look at our for our negative result for our among people that don't have nickel sensitivity. So that's 90%. So 90% of the time, you will get the result correct for those 195 people in this sample that do not have nickel sensitivity. So let's see, 195 times 0.9 is equal to 175.5. Okay, it's okay for us to be working with 175.5. So I would get that right about 175 times out of 195. I would get that correct. Now, how often would I get it wrong? Well, it's going to be the difference between 195 and 175.5, and that's 19.5. Okay, whoops. Okay. Maybe I should have stuck with 5%, right? Because I would have wound up with even numbers then. Okay, but trust me on this, it's going to work out. It's going to work out just as well in the end. Okay, so now how many people in this population tested positive? Well, in this particular group, 23.5 people tested positive, and 176.5 people tested negative. And these should add up to 200, as I hope they do. Yes, they do. Okay, so now looking at this, what's the positive predictive value in this case? It's going to be how many people tested positive? 23.5 people tested positive. 4 of them had the disease, 19.5 didn't. So the positive predictive value was only 4 over 23.5, okay, which is going to be equal to is only 17%. So if you test positive, same test we did before, if you test positive now, the probability you actually have the disease is only 17%. Well, that's interesting because before, the only difference was the prevalence. The test's exactly the same. The only difference was the prevalence in the population. And what was this again? I think it was 0.67%. Right? Only thing that changed here is the prevalence. It's exactly the same test. Okay, so what does that mean? Right? When you do pap smears and you test an entire population of women for a relatively low prevalence cancer, right? Even if the pap smear is not very, they don't have a very particularly high sensitivity and specificity anyway. But if you test an entire population of women and the prevalence in the population is only 1 in 100 or 1 in 1,000 of people that have that disease, what are you going to wind up with? You're going to wind up with a lot of false positive. Same thing with mammograms. I'm sure you know plenty of people that had a positive mammogram, they have a biopsy, turns out not to be cancer. Because we have this issue with applying diagnostic tests, as good as they might be, to diseases that have a relatively low prevalence in the population. So with men, we have that issue with PSA tests, right? It looked like a good way to screen men for prostate cancer, but among men within a certain age, the test had a relatively low specificity, so you get a lot of it's a low within the ages that they started testing people, like say 40 to 60. It's very relatively low prevalence of that disease, and the test didn't have great specificity and sensitivity anyway. So you wound up getting a lot of false positives and a lot of biopsies and so on and so forth. A lot of invasive procedures wound up being done based on a test that maybe the test could be okay, but that the prevalence in the population was low enough that they wound up doing a lot of unnecessary procedures. So nowadays, doctors are getting more and more conservative about this stuff. 10 or 15 years ago, there was everybody was pushing tests at a certain age. Everybody should be screened at this age. And now you'll notice that they're pushing the age up typically as they realize that these false positives are causing a lot of injury from unnecessary procedures that wind up going wrong and stuff like that. So you guys how is that? Do you have a handle on that? Does this make sense to you? This relationship between sensitivity, specificity, and positive predictive value. Okay, good. I just want to mention one other thing that we get from these numbers that may come up at some point or another, just so you know about it. Not used quite as much, but that would be the negative predictive value. So in this case, the negative predictive value is if you get a negative test, how likely is it that you don't have the disease? Just the converse of the positive predictive value. So you have 176.5. I'm going to do the other one first. It's going to be simpler. So in this case, we have 150, the negative predictive value, right? It's going to be equal to, let's see what we have here. We have 152 people that tested negative, 144 of them actually are negative. So out of 152, 144 are negative. So our negative predictive value is going to be 144. To be clear, 144 divided by 152, okay, which is 95%. So if you get a negative test, you're 95% certain that you don't have the disease. right? Let's take a look at how it's impacted by a lower prevalence. Okay, in our case, um, 176.5 people test negative. 175.5 of them actually are negative. So 175.5 divided by 176.5, right? What's happening there? It's having the opposite effect, isn't it? Lower prevalence that you have, the less likely that you're going to get false negatives. Okay, where my calculator go? Negative predictive value in this case with a lower prevalence is going to be 175.5 divided by 176.5. Okay, 99.5%. Good. You guys, I glanced. Yeah, I should wait for you to do it before I actually do this because you're actually getting done ahead of me. Okay, so really that's kind of what we're dealing with in this case. So now I'm going to take it another step. The positive predictive value is what you get. What's the probability that a person has the disease under what condition, given that something else has occurred, that he's tested positive? What did we call that about a half hour ago? What were we referring that as? That's a conditional probability, right? How could I describe that? Okay, that's the positive predictive value is the probability that a person has the disease, given that bar is basically the same thing as saying given that he's tested positive. This is a conditional probability. Given that he's tested positive, how likely is he that he has the disease? And that's what the positive predictive value, same thing, right? Okay, so let's take that to the next step. You remember we were talking about something called Bayes' theorem, which is a simplified way. I hate to call it a simplified way because it's going to get complicated, right? But it's a way for us to calculate a conditional probability given without doing this hodgepodge with a fake population and just using the data that we actually know about a population. So I'm going to step back a bunch of slides. Okay, and we'll get a couple of ugly formulas up here that we'll step through. Here's Bayes' theorem, okay? Probability of A occurring given that B has already occurred. Now, there's a derivation that Levi started to go through on the using the Venn diagrams with probability, where you could kind of like figure out, well, you're talking about this area over here and this circle and this part of this circle and this is divided by this, and if I combine these, if you step through those Venn diagrams carefully and analytically, you'll actually be able to figure it out if you want to. You don't have to. You just really, as far as we're concerned, you need to be able to apply it more than actually understand the derivation of it. But if you really went through it carefully, it would make sense to you. But what is this? Probability that the probability of A occurring, given that B has also occurred, that B has occurred already, is equal to the probability of A and B over the probability of B. Okay, so now you can do the inverse. Okay, probability of B occurring, given that A has already occurred, is the probability of B and A over the probability of A, right? Just you can reverse those letters, because it doesn't matter what direction those letters in, but once they start to represent something, then this has a lot more meaning. So I'm going to move on to here. Okay, let's take a look at this. Okay, now here is the formula in its raw form. Now I'm going to take that and apply it to the positive predictive value. So what is the positive predictive value? The positive predictive value is the probability that you have a disease given that you've tested positive for that disease. Okay, so remember when I did this in the contingency table, the number I put on top was the number of people that tested positive that really had the disease, and the number of people and the bottom was the total number of people that tested positive, including the ones that didn't have the disease. So this is really the number of people that tested positive and had the disease over the total number of people that tested positive. Hence our positive predictive value, the way we did it with that table. Well, how does that relate to this mess that we have over here? Okay, well, let's look at this very carefully. The probability that you test positive given that you have the disease, what does that mean? Anybody have an idea where we might have seen that already? What's the probability that you test positive given that you have the disease? What did we call that before? There's a name that we gave that. Oh, that's a true positive. That's a true positive. Yes, but yes, it's the sensitivity, right? The probability that that you test positive, given you have the disease. Like in other words, this would be 80% for the nickel test that we were looking at. You would test positive 80% of the time, given that you have the disease. So this is 80%. Okay. Now multiply that times the prevalence of the disease. Now, when the prevalence, this is 80%. When the prevalence of the disease was 20%, right? Well, then the probability you test positive, 20% of the population has the disease. The probability that you test positive if you have the disease is 80%. So 80% times 20% is going to be 16%, right? 16%. So that means 16% of the population that tests positive and has the disease is up here. So this is the top part of that equation. And what is the probability? What is this probability of having the disease? What's another name for that? Probability that you have the disease. What do we call that in a population? Probability someone has diabetes. That's the prevalence. So what is this on the top here? This is the sensitivity times the prevalence. Okay, now let's go to the bottom. The bottom's going to get a little bit more complicated because it includes everybody. That this is only the people that tested positive that actually have the disease in the population. Bottom is going to be everybody that tested positive in the population, whether they had the disease or didn't have the disease. In other words, the true positives and the false positives are on the bottom, just like we did before, just like we did when we were using real numbers before. Okay, so let's look at this first part. Probability that you tested positive, given you have the disease, times the probability you tested positive, probability that you have the disease in the population, sensitivity times the prevalence. That's exactly what we have on top, which is, as we already determined, the proportion of the population that is a true positive. Okay, now this second part then, if you can imagine, is going to be the people that test positive that don't have the disease. In other words, they're the false positives. So how do we get to that? Okay, well, the probability that you test positive, given that you don't have the disease. Okay, probability that you test positive, given that you don't have the disease. Let's see, you don't have the disease, but you test positive. That's a false positive. Times the probability that you don't have the disease. Well, this is 1 minus the prevalence, right? So the probability you test positive, I'm going to move over to this next version of it so we can see this. The probability that you test positive, given that you don't have the disease. Well, if that had been the probability that you don't test positive, given you don't have the disease, it would be the specificity. But it's the probability you test positive, given you don't have the disease. So that's 1 minus the specificity, right? It's the inverse of the specificity. Times the probability that you don't have the disease, that's the prevalence. So let's think about that. The total number of false positives, the proportion of the population that are false positives are, well, first of all, they have to be people that don't have the disease. So the prevalence was 20%. So 1 minus 20% is 80%. So we're starting off with the 80% of the population that doesn't have the disease. So now we want to know 80% doesn't have out of those 80% of the population don't have the disease, right? How many of those people test positive? Well, if the specificity tells me what proportion of them test negative, because that's when it's right. So if I wanted the true negatives down here, I would just multiply specificity times 1 minus the prevalence. But I want to know what proportion of them tested positive that didn't have the disease. So instead of 90% being right, it's wrong 10% of the time, or 1 minus the specificity. So what proportion of this population is a false positive? It's 1 minus 90%, which is 10%, times the prevalence, 1 minus the population and the prevalence in the population, and which is, actually, let's actually do this. I wonder if I got it. I don't know why I'm actually not even just using the numbers. Let's do it right now. Okay, let's actually do these numbers, and it might even be a little bit clearer. Whoops. Get rid of this over here. Make that go away. Good. Okay. Okay. First of all, I'm gonna fix this here. This is a probability that you have the disease, given that you test positive. Okay. Okay. So what is that going to be equal? That's equal to the sensitivity, which is 0.8, times the prevalence, which is 0.20. I'm doing the first example because the numbers are a little easier. Divided by the sensitivity, right, which is 0.8 times 0.2. Again, this represents the proportion of the population that tested positive that really has the disease. In other words, true positives. Plus the other people that tested positive are people that don't have the disease, right? So it's going to be 1 minus the specificity, which is 1 minus 0.9, which is 0.1, times 1 minus the prevalence, which is 0.8. Yes, 0.8. Prevalence is 20%. 1 minus that is 0.8. So let's work this out. That's 0.16 over 0.16 plus 0.1 times 0.8 is 0.08. Is going to be equal to 16.16 over 0.24. What's that equal to? 0.67, right? 67%. Guys, remember what we got for the prevalence before? So you can employ, if you have an example where all you have is the you don't have to go through this whole thing. If you know the sensitivity, the specificity, and the prevalence, you can use Bayes' formula to calculate the positive predictive value, right? Pretty simple once you know how to do it, right? And that's the derivation of this. That's really what this is just, you can reason it out. These are on the top of the equation is the total number of people that are true positives, the proportion of the population that test positive that really have the disease. And at the bottom is the proportion of the population that tests positive, whether they have the disease, which is this part, or don't have the disease, which is this part. True positives, it's true positives on top over true positives plus false positives on the bottom, just like it was when we actually pulled the numbers out of that table. Okay, so okay, let me see what I got back here. Bayes' theorem. Okay, so I'm going to move this out of the way. So are you guys okay with that? Does that make sense to you? In fact, I think we actually have let me find it here. Here's an Excel spreadsheet where this has already been, I'm going to blow this up a little bit, actually, to get to it a little bit more easily. Let me spread it out. 200%. I'm pretty sure we got this set up right. Okay. So this has already been set up so that in this cell for positive predictive value, in other words, the probability you have the disease given that you test positive. Okay, this has already been set up. If I click into this cell, you'll see that the formula up top, well, actually, before I get to that, let's look what's in, this is a population, these are just numbers that are in here. This is a population. What's the prevalence of this population, for starters? Anybody tell me what the prevalence of this population is? Okay, yeah, 20%. 200 people have the disease out of 1,000 people that's in this sample. Okay, what's the sensitivity of this test? Well, out of the 200 people that actually have the disease, right, 170 of them test positive. That gets it right 170 out of 200 times. Well, if I click in here, you'll see that this is the way that this has been determined is it says, okay, D8, which is 200, divided, let me see what they did here. I'm sorry, the prevalence is 200 over E8, which is 1,000. So that's how they got that number. Okay, well, how about the sensitivity? If I click in there, that's D6 divided by D8. D6 is 170 and D8 is 200. So if I look in here, I can tell 170 over 200, the sensitivity is 85%. 85% of the time, it identifies people that actually, these 200 people, 85% of the time, it actually identifies the ones that have the disease and gives them a positive test. Well, how about people that don't have the disease? 800 people don't have the disease. It gets it right 720 times out of the 800. So the specificity would be 720 divided by 800. And in fact, if we click in here, we'll see that it's E7, which is 720, divided by E8, which is 800. So an interesting way to use Excel here to do this calculation. Okay, so now let's say, nice thing about Excel, you can do a lot of what if stuff. What if the prevalence was not 20%, but let's say the prevalence was only, escape. What if the prevalence was only, what's the easiest way for me to do this? This is actually, it should have been 200 and then calculate these things up that direction. Would have worked better. Matter of fact, I'm going to do that right now. I'm going to put 200 in here. Oops. Nah, I shouldn't monkey with it. Okay, let's say that that this was actually I hate myself for doing this now. Let's say there were only 20 people. Oops. Let's say there were only 20 people that had the disease out of the 1,000, right? So that would be 3 and 170, right? And so now the prevalence would be, instead of being 20%, the prevalence is 2%, right? So here's the prevalence down here. Okay, 20, kind of odd. D8 plus E8. Oh, you know why? Because 20, that many don't have it. How many will have it? This is going to have to wind up being, the way this is set up, it's not going to be comfortable for me to do this, unfortunately, because I'd have to, the way it's been calculated here, I'd have to redo this whole thing. Let me see. It's a good way to do this. I'm going to redo this right now. What the hell? Okay, let's say that this is equal to 200. No, you want that. Say this is 800. So you can actually maybe it's a good exercise just to watch me monkey with this thing. Okay, so the prevalence is going to be equal to D8 over, it's going to be equal to D8 divided by F8. I'm going to do it slightly differently. Okay, there's our prevalence, 20%, 200 over 1,000. And this is equal to this, oops, it's equal to this minus, it's equal to this minus the 200. Okay, so now, and this is equal to this. I'm going to mess this up. It really wasn't set up to do this, unfortunately. Okay, I really shouldn't have gotten into like changing the prevalence on this because the table's not really set up for that. All right, so anyway, you saw how the prevalence was calculated based on this table. I'll close this and reopen. I'm going to make a couple of these on Excel, so it works a little bit better depending on whether you want to manipulate the prevalence or the actual values. Okay, good. Let's go back to this. Here's the prevalence. These numbers are based on this table. So I'm going to ignore that for a second. I'm going to go down to the positive predictive value. Positive predictive value, remember the way that we calculated this. On the top is going to be the proportion of the population that tests positive and actually has the disease. So D11 times D10. So what is D11? D11 is the prevalence times the sensitivity. Okay, 0.2 times 0.85. That's the proportion of people that test positive that actually have the disease. Okay, D11 divided by D10 times D10. Sensitivity. See, the sensitivity here is 85%. I'm just going to use these here. 0.80. Okay, sensitivity of the test is 80%. The prevalence of the test is 20%. So 67% of the population, positive predictive value is 67%. So we know that's right, but we've done it before. Okay, so if I click back in here, how do we get that 67%? By applying Bayes' formula. Well, in Bayes' formula, if I look at this very carefully, it's actually it looks at D11 first. The sensitivity times the specificity is the top part of the equation. The bottom part of the equation has two parts. Okay, the first part is the same thing. It's the proportion of the population that tests positive given that they have the disease. In other words, the prevalence times the sensitivity again. Okay, plus the proportion of the population that the specificity, 1 minus the specificity times 1 minus the prevalence, 1 minus the 1%, 1 minus D10. So this formula does exactly what the Bayes formula that we derived, that we employed before, except in this case, I can actually manipulate remember we also did the negative predictive value and we got this number as well. But in this case, I can actually just work from the prevalence, the sensitivity, and the specificity, and it'll determine the positive predictive value. Like for instance, we changed the prevalence to, and actually I can just go ahead and change the numbers. I don't have to use the formula. If I change the prevalence from 20%, 0.2 to 5%, okay, you can automatically see the change in the positive predictive value. I'm gonna set this up a couple of ways, this table, so that you can use it a little bit more effectively. Okay, if I undo that, no, I can't undo. Okay, I'm gonna go back to a prevalence of 20%. What happens if I alter the sensitivity of the test? What if the sensitivity of the test is 90%? Okay, how does that affect the positive predictive value? Not as much as the prevalence does. It's much less of an influence on the positive predictive value than the actual prevalence. Okay, what about negative predictive value? It's already 90%. Let's make it 99%. See what how that affects the positive predictive value or the negative predictive value. Well, that helped a lot, didn't it? The reason why it helped a lot is because it's the specificity is eliminating an improvement in specificity when the prevalence is pretty high, when the prevalence is high, is eliminating a lot of the false positives. So that's what's affecting both our positive predictive value and our negative predictive value. I almost regret having opened this spreadsheet up because it wasn't set up quite the way I anticipated. So I'm afraid I might have confused some of you. So what I'm going to do is I'm going to make up 2 or 3 spreadsheets that'll work differently. One where you can actually manipulate the numbers in the table, and another where you can just work from this prevalence, sensitivity, and specificity to calculate the positive and negative predictive value. Now, when we have the exam, you will be allowed to, it's an open book exam. You can have your book. You can have any notes you want. You can have, we're going to be doing them in class. You can have access to anything that's on Blackboard, the PowerPoints, the materials, the answers to homeworks, the so on and so forth. You have access to all of that material. You're not allowed to go surfing around the internet for information, though. You have to confine yourself to what's on, what materials that we have associated with this class. And that will include, for instance, if I go onto the internet right now, I can see if I can't find a positive, predictive value calculator. Diagnostic Test evaluation calculator. Here we go. Now let's see what we got here for true, false, positives, and so on and so forth. Okay, this is actually if you put the actual numbers in here. Let me see if I can't find one that's just going to work with Bayes' formula. Nope, this is an explanation. I'm looking for a calculator. Positive value, Bayes. Okay, let's see if I can't do it here. Positive predictive value is 0.8. Negative predictive value is 0.9. Positive likelihood ratio. Pretest positivity. Nope, still. Oh, hang on a second. Let's do this up here. Prevalence was 0.2. Sensitivity was 0.8. The specificity was 0.9. And let's do our calculation. Bingo. So you did what I did with a population, the pseudo population of 1,000, and it calculated a positive predictive value, negative predictive value, and so on and so forth, and filled in this table for us. So it did this. It literally did what we needed to do this. It used the Bayes' theorem to use the prevalence, sensitivity, and specificity to calculate all these other evaluations of this test that we're interested in, particularly this conditional probability, positive predictive value, and as a bonus, it also calculated the other conditional probability we're interested in, negative predictive value. What's the probability that you don't have the disease given that you've tested negative? Okay, so you could use something like this, but on the exam, presumably I'll supply you with a spreadsheet which pretty much works the same way that this one does. And in fact, that's probably a better way to do this, right? For me to give you those to fill in and have it fill in the rest of the tables. A little bit more rational way to do this, make it easier to alter these values. Are there exams, written exams versus online? Are the exams written exams versus online in class? The exam will consist of basically the way that you do the homework, where it's a test that's on Blackboard that you can fill in. Some of it will be multiple choice, some of it will be short answer, some of it will involve some calculations where you'll have to go to SPSS and copy over a table or a graph or something like that, maybe do an interpretation. But as we get closer to the test, I'll start to fill you in on what the problems will look like. I'll give you some examples of the types of questions that are likely to appear on the test, and also I'll probably do a couple of extra sessions online, probably a few days before the test, so that if you have like review sessions, so that you have questions or something like that, we can review those. I'll tape those review sessions as well. So if there are times that are not convenient, you can watch them afterwards as well. Okay, so it's about 8:15. So I'm gonna give you guys the next 5 minutes off. So kind of like a vacation. So if you have any questions that you have, guys. So is this until I screwed up the last part of this? Was this pretty clear? Okay, you guys pretty comfortable with this idea of diagnostic tests, positive predictive value, sensitivity, and stuff like that? Is this new for you guys? Have most of you guys seen this before? Or is this something that is a new concept to you? Have you ever wondered if you have a diagnostic test, have you ever wondered how certain it is that if you get a positive that you really have the condition that they're checking you for? And remember, the first diagnostic test is usually very simple. It's a screening test. So it's non-invasive, it's inexpensive, it's quick. And then if it's positive, what happens? You get sent for usually a more expensive or invasive test or something like that. Okay, good. A lot of this negative predictive value, positive predictive value is new for a lot of you guys. Let's just take a quick look here. Let me just do another quick search here. Positive predictive value for PSA. See if they say anything about screening for prostate cancer. The overall, I saw it there. I'm going to go back because it was easier to find before I clicked into the article. The overall positive predictive value for a PSA greater than 4, right, the nanograms per milliliter, is approximately 30%, meaning that slightly less than 1 in 3 men with elevated PSA will have prostate cancer detected on biopsy. Pretty interesting, right? Okay, how about positive predictive value for uterine cancer? Let's see, sensitivity, blah, blah, blah. Clinical evaluation, positive predictive value of 14.8%, right? 85% of women that test positive don't have that disease, right? So interesting. When you apply these tests, even if they're good tests, you apply them to a low prevalence condition, you can wind up with some very disturbing results in terms of what winds up happening in terms of more invasive testing and so on. Okay, so you might, if you next time you're in a clinical environment, you see somebody employing a clinical test, a diagnostic test, say to yourself, yeah, I wonder what the predictive value of this test is, and go ahead and look it up. See if it's better or worse than you would imagine it would be. Okay, so okay, guys, good night. I'll see you guys on Monday. I'm going to post either an exercise or a homework. It actually in the syllabus, I think it says that the next homework is posted on this class coming up. But maybe I'll get it up there a little early so you have a little bit more time to work on it. That includes some problems that involve probability and these diagnostic tests. There might be a portion of it that includes stuff that's in future weeks. So if you get started on it, don't be upset by the fact that there's things in there we haven't covered yet, because I'm going to give you a lot of time to get it done by posting it a little early. Okay, guys, so good night. Nice.